for coming to class. Today we're going to be talking about some of your reading, and then we're going to be doing a POCHL, and we're going to, we're learning, and as you read, we're going to be sort of learning about some of the basics of computer programming languages, and then we're actually going to start learning them. Python is the language that we're going to be learning in this class, and it's what we call a high-level language. And the reason it's a high-level language is because it's a language that humans can understand. If you actually looked at the language that the machine understands, it would just be a bunch of numbers. And it would be very difficult to program with just putting numbers in, right? You might have a number that means add, you might have another number that means jump to a different place in the program, you might have another number that means compare two numbers. And so rather than do that, we write things in a higher level language that makes sense to humans, and then we let somehow that program has to run on the computer. Now it turns out there's two ways of running a program on a computer that is a higher level language, because the computer doesn't understand the higher level language. The computer doesn't understand Python. Turns out it doesn't understand any language other than its own, right? You can't, and so how do you teach a computer to understand a higher level language? Well, we make a program that does that. And so there's two types of programs that allow a machine to run a high level language. One is something called a compiler. A compiler is like a translator. It translates it from the high level language into the machine's vernacular, right? This is like when you read a book, like let's say you were going to read a Dostoevsky novel, unless you're fairly fluent in Russian, you don't buy the Russian version. You go buy an English version that some translator has taken a considerable amount of time to carefully translate from Russian into English, right? And that's a translation process. They only have to translate it once, but then many, many, many people can read it. Now that's not what Python does. That's what the language we're going to be learning in later in this class called C++ does, but Python doesn't do that. Python does something called an interpreter. Now we've all heard of interpreters in human languages before, right? Sometimes maybe you go to hear somebody talk who doesn't speak your language, and so they have somebody standing beside them. They say a sentence, the interpreter tells you what they said in English. They say another sentence, the interpreter tells you what they said. That's kind of like what Python does. Python basically looks at your program line by line and then figures out what it's supposed to do and then does it, right? Ultimately, Python is written in machine code, but it can understand Python. Oops, sorry, I went to the wrong page there. So when we use a compiler, there's this process where we have we have our code that we write, that humans write, that humans understand. We run it through a compiler, which translates it into machine code, which is horrible to look at. That is loaded into the CPU of the computer, and then it can run. So we translate it just like we translate a book from one language to another. Now a translator takes a program, and there's a special program, of course, written in machine language that interprets the source code and uses the computer to interpret the source code and do what the program wants to do. Now, it turns out that compilers generally, programs written in a compiled language generally run faster because they don't have to be interpreted every time you run it. They can just run in the native language of the computer. Whereas when you run with a translator, you have to figure out what the program wants every time you run it. And so it's slower. Now, ultimately, computers are machines, and they're complicated at one level, but at another level, they're fairly simple. They only have a fixed set of instructions that they can operate, and those instructions aren't that complicated. Okay, so but they are machines. Now, it turns out there's two types of computers. Computers that have the program baked into them and they only ever run one program, like a calculator or your microwave oven, right? It doesn't change. The program always does exactly the same thing, or the thermostat on your wall. Now, stored program computer is a computer where you can put new programs in it and make it do different things. Your laptop is that. It turns out your phone is that, right? You can download new apps. So what does a computer look like if you could peer inside of a computer? Now, you wouldn't actually see this because this is a logical rather than a physical representation, but of showing that how a computer is made out of components, just like a car is made out of components, right? An automobile has wheels, and it has an engine, and it has a transmission, and it has a steering wheel, right? And it has these different parts that work together to make a car do what a car does, which is move people around. Well, a computer has to have memory. Memory, not surprisingly, is where we store things. Then it has what we call the CPU, which is kind of the central, which stands for the central processing unit, and it's the brains of the operation, and it's got two pieces. It's got the control unit and the arithmetic logic unit, or ALU. So what happens? The control unit pulls numbers, which are instructions, out of memory, and then it executes those instructions. Now, if those instructions are, for example, an add instruction or a multiply instruction or a divide instruction, it uses the arithmetic and logic unit to do the work of that instruction does. It's at a very low level, though. Then finally, CPU is somehow connected to the outside world so that you can hook it to a screen or a keyboard or a mouse or a microphone or a speaker or the internet to get data in and get data out. So the fundamental amazing thing about a computer is that it uses something called a stored program, right? It's not fixed. You can write new programs for it, and then you can put them in to the memory. And once a program is in the memory, the computer can little by little execute that. It can follow the set of instructions, much like you follow a set of instructions when you bake a cake and you're looking at what you need to do to mix and bake that cake, right? You follow a set of instructions, and you can follow different recipes. A computer can follow different programs just by putting different programs into the memory. And so it turns out when you run a program, what literally happens is it takes a program out of a storage device like a disk or some sort of flash drive, moves it into memory, and then it goes through and executes that program little at a time. In fact, it turns out a computer has a special baked-in program called the interpreter that actually does the process of fetching an instruction, executing it, fetching the next instruction, and executing it. Now, the thing about programs is for them to be useful and for them to actually work, they have to be well defined. Now, it turns out that Alan Turing, who some of you may have seen him depicted in various movies recently, he was very, important and now famous mathematician from England, who, among other things, cracked some of the Germans' codes for that they were using to communicate with, and he came up with some of the fundamental theories of computation, and he showed that you can do anything any computer can do anything that a computer can possibly do with only 6 primitive operations. Now, we're not going to talk about what those are, but you don't need very many different things to do anything that a computer can do. And what more importantly, he showed that there isn't some other magic instruction that you could add to a computer that would make it do more. That's enough. Now, modern computing languages have many more than 6, because we want them to be easier to use. Now, it turns out that languages are only a matter of convenience. There's thousands, there's probably tens of thousands of computer languages. They all do the same thing. You only really need one, but some of them are easier to do certain things in than others. Turns out Python is a fairly easy language to learn, and that's one of the reasons we're learning it in this class. Now, when we talk about languages, we know all about some languages because presumably everybody in this class knows about English. Some of you guys may know about Chinese or Spanish or French. Now, or maybe Zapotec. Who knows? I don't know what languages you guys know. Now, of course, we know that languages are made out of what we call primitives, right? A language has things that we build things out of, like little bricks. And in English, that's words. We have lots and lots of words, and then we put those words together to build sentences that have meaning. In programming, we have, instead of words, we do have words, but we have different types of words. We have numbers. We have things called strings, which are like words. Those are characters. And we have something called operators, which are things like plus and minus and equals, which tells us what to do with other things, okay? Now, the thing about languages is language has two major components that we oftentimes talk about: syntax and semantics. You heard those terms before? Syntax and semantics, or is that new? So syntax is the structure of how things are supposed to fit together, right? And English has a syntax. So for example, you can say cat hugs boy, which is kind of a weird sentence, but it actually has a valid structure. You know that we have a noun, a subject, a verb, and we have another noun, and which happens to be an object. And what we're saying is that the hugs verb is being done by the subject to the object, right? That's the way hugs worked, right? So the syntax, of course, of English generally is we have things like a noun, a verb, and another noun. You know, sometimes we have just a noun and a verb. Sometimes we have a noun and a verb and another noun and a prepositional phrase, right? There's different ways we can build sentences out of words. Ones that that follow the correct syntax are called syntactically valid. This isn't syntactically valid. It could never, cat, dog, boy doesn't work because you can't put three nouns together in English and make a sentence. It's just not allowed, right? A programming language is the same way. Quote, high, quote, 5 just doesn't mean anything. It's not the right way to put things together. Whereas 3.2 times 5, what that means is take 3.2 and multiply it times 5. It doesn't matter what it means, though. The point is it's a valid construction. So one of the things we have to learn when we learn how to program is, just like we had to learn when we learned English, is we have to learn what are the right ways we can assemble things together to get something. That's called syntax. Now, it turns out there's another aspect of language that I mentioned earlier called semantics. And semantics is about what a language means, right? So we know that this is syntactically correct, not because we use the word hug and cat and boy, but because the right sorts of things, nouns and verbs, are used in the right order, right? There's lots of sentences that have the same syntax that mean something different, like boy eats pizza, right? Or girl runs race, right? These are combinations that make sense, but they mean different things. Now, semantics has to do with a higher level than just syntax. It's how things can be put together in ways that mean something, right? So for example, in English, we can say, I am hungry. Turns out this is syntactically correct, but just as importantly, it's semantically valid. It's the right way to do things. Now, maybe somebody who is just learning English might accidentally say, I are hungry. And we'd say, no, you aren't are hungry, you am hungry, right? Because what's going on there, right? So it turns out that this is a verb, I'm sorry, this is a noun, a verb, and an adjective. But the point is that we've put things together in a way that don't work because the noun, the verb is supposed to agree with the subject, and this is singular and this is plural, right? So we can't put a singular subject with a plural verb. So we need to say, I am hungry. So it's, although it's syntactically valid, it's semantically invalid because they don't work right together. We have that in programming language as well. For example, 3.2 times 5 makes syntactic and semantic sense, right? We're multiplying two numbers together. 3 plus high is semantically correct because we're adding two things together, but it doesn't make any sense semantically because you can't add 3 to 5. Why not? Well, we'll talk more about that later. Okay, so semantics is the meaning associated with syntactically correct string of symbols with no semantic errors, with no static semantic errors. So for example, in English, we can have, now, not example, but in English, semantics is really tough sometimes because we have ambiguity, right? Somebody can say to you, flying planes can be dangerous. And one person will think to themselves, yes, it's dangerous to fly in a plane. Or flying planes can be dangerous because they might crash and hit somebody, right? So they're dangerous things. Planes are dangerous things. But they could also mean the act of flying a plane is dangerous. That's a different meaning. Same words, different meaning. I saw the girl on the hill with a telescope. What does that mean? Well, it could mean that you saw a girl up on the hill and she was using a telescope. But it could also mean you saw a girl on a hill by you using a telescope, right? It depends on where with the telescope attaches. Does it attach to the girl on the hill or to the I saw, right? And so those are two different interpretations. Now, in English, we have that. In programming languages, we never have ambiguity. Programming languages are designed to not be ambiguous. It will only ever do one thing. So where things go wrong, right? We're going to learn a lot about where things go wrong. And the reason I'm spending so much time talking about this is because you're going to write stuff and it's not going to work. And you're going to say, why doesn't it work? And that's basically what fixing or debugging a program is all about, is you try to do something, but you don't get it right. And you have to keep working at it, right? Because it turns out that, like if I were to say to you, I are hungry, you would say, boy, he's a little dumb when it comes to talking, but I'll go get him some food, right? Computers aren't that way. If you say something wrong to a computer, it just says, sorry, I can't understand that. So what are the ways a computer program can go wrong? Three major ways. One is you put the words together and it will tell you, I'm sorry, that doesn't make any sense. Or you can put the words together and it's the right sort of order, but it still doesn't make any sense because you're putting the wrong things next to each other. It can tell you that. But the third type of full semantic error is you might write a program and you might write it wrong, so it does the wrong things, right? And so that's a little bit harder because the program will run, but it's not doing what you want it to do. For example, if you write a program to compute square roots and it doesn't compute the square root, it computes some other number, it's not right. The program runs, it's syntactic and static semantically correct, but it's not what you want. Right? So, and we can see this sort of thing in English because I could say to somebody something And I'm trying to think of a good analogy here. So certainly, if I don't fully understand English, I might tell somebody something that makes sense to them, but it's not really what I want them to do because I use words incorrectly, right? So, um, you know, um, so anyway, we see this in programming. Sometimes a program will run and crash. It literally stops because you told it to do things that it's not allowed to do. Or a program could get stuck running forever. We call that an infinite loop. Or a program could give an answer that's not what was expected, right? It gives the wrong answer. So the goal here is to learn syntax and semantics of a programming language and to use those elements to translate recipes, something we call algorithms, for solving the problem into a form that the computer can now solve the problem for you, right? So I could teach you, for example, on paper, how to come up with a square root. And then you could say, you know, that's a lot of work. I'm going to write a program to do that for me, right? And you can do that with lots of different things. So then we're going to also learn computational modes of thought to enable us to leverage a suite of methods to solve complex problems, right? That's where computers really make sense, right? Now, let me just say one other aside here. You can't teach the computer to do something that you don't understand how to do yourself, right? Somebody could say, in other words, if you have some idea and you say, I want to make the computer do it, the first thing you have to do is figure out how to do it yourself, right? If you can't solve this problem yourself, if you can't on paper do the solution and monitor how you're doing it, then you can't teach a computer how to do it. Which, by the way, this is one of the reasons why computers aren't very good at, for example, communicating with us in English, because the interesting phenomena about human languages is that people don't know how they use how they use human languages. They just use them, right? It's not easy to tell it's very difficult for us to tell a computer speak English to write a program to do that because we don't know how we do it ourselves. Human languages are very complicated and they're tied directly into the brain. Okay, so Python programs. So a program is a sequence of definitions and commands. You define things and then you give commands to do things with the things that you defined. And so the commands instruct the Python interpreter to do certain things. Okay, so what time do we have here? Okay, I want to leave time for us to do our POJL. So I'm going to stop here. And because now we're getting into Python and I want us to do, I don't want to, but by the way, I never want to talk too long in this class because I don't want to bore you to death. Okay, so we've talked for a while. What we're going to do now is we're going to go to today's syllabus and we're going to do in groups just like we did last time, right? We're going to do this POJL. Okay, so now here's the way it's going to work. Just like before, I'm going to divide us into groups. You're going to go into your groups and you're going to decide who you're going to somebody is going to make a copy of this document. You're going to share it with each other and you're going to share it with me. And then you're going to decide what your roles are. And you are going to use REPL, and I talked to you about how to do this as you read through the instructions. So I don't want to say any more because the rest of everything's in there. So I'm going to break you up and we're going to, and make sure to think about your roles. Make sure to think about your roles. Okay, so let's stop the sharing. Okay. Now I'm going to break us into rooms. Here we go. Huh. Now that's weird. Oh, there. No, I see it. Okay. We're going to have a lot of groups today. Wait. No. Wow, we have to have 8 groups? Phew. It's a lot. Okay, so here we go. Now you'll see a thing for where it'll be inviting you into a room, and you each need to go into your rooms.
Oh, hey, we were wondering if we're supposed to have a 4th person. Is it just the 3 of us?
No. Okay, so yeah, your group's group 7, which means, right, if we don't have a multiple, we have 29 people, so we don't have a multiple of 4. So there's going to be a couple of rooms with 3. And so in that case, somebody should be the spokesperson and facilitator.
Oh my gosh. Okay.
Okay.
Thank you.
Yep,
Thanks.
Bye-bye.
I volunteer as process analyst.
Yeah. Hmm.
Wait, that's bizarre.
Hey, how you guys doing?
This is
Did this
tricky.
work? We're
It's probably
unable
supposed
to. The commenting out the lines isn't working, and we're getting stuck on a line that isn't there.
Right, I mean,
Oh wait, no, this worked. We got it.
Oh, we got it.
Did you
Oh,
Yeah,
guys share
the slash n starts a new line.
Did you guys
But yeah.
share your Google Doc with me? Because I don't see it.
Oh, I thought we did. Let's double check.
Let me see.
Yes. Unless I got the email wrong.
Yeah,
No, it's gone. Yeah, it's there.
it's team 1.
Okay, okay, team 1. Okay, so see if I can find it.
So this prints.
Okay, I'll see you guys later.
Sounds good.
Yeah, I like this is very kind of I don't know, this is like it's just because it's not a syntax error, but like it just doesn't make sense in English. So to us it's a
Yeah, it's just
error.
different input. That's the question. That's the answer to number 2 because there's different inputs for A and C.
Yeah,
How you guys doing?
Well,
we're doing okay.
Okay, just checking in to see if you have any questions.
Thank you.
Okay,
How are you doing?
oh, pretty good.
Wonderful to hear.
I'm jumping around. I got eight groups. So
Yeah.
I'm gonna jump to the next one. So see you guys. Just send me a message if you need anything.
All right, thank you.
All right,
Okay.
thank you.
Thank you.
Bye-bye.
Does what I'm trying to express, does it make sense though?
Hi, Professor.
Yeah.
Hi, how you guys doing?
We're good. I think we just have a question on one of the questions in the file.
Yeah, I'm looking at your thing. I actually have two. But
Okay.
yeah, what's up?
For part one, part C, it is like a print hello /n. My name is Bat. Okay.
Mhm.
So is this like a semantic error? Because if I want to print /n, my name is Bat, to be like an output, are we supposed to say semantic error or it's not?
No, it should work. Didn't it work for you?
It did.
It worked, but
Yeah.
it like if I
Hold
want
on.
like a print /n and
Didn't print the /n, right? It should have put it on a different line. Did it do that?
Yeah.
it did.
did it.
Yep, that's exactly what it's supposed to do.
Oh,
Oh, okay, cool.
Think about that.
Cool.
Yeah. Okay. Any other questions?
No, I think we're good.
Or the-
There's confusion there.
Yeah.
yeah.
Okay. Well, you guys are doing good. You're working together. And I will.
Yeah.
Okay.
Mhm.
See ya. Bye-bye.
Terrific.
Of containing 3 statements.
So how's it going, guys?
I think we're going at the right speed.
You think what?
I think we're going at the right speed.
Good. And making
Only on the application questions.
Okay, good. Good work. Okay. Just checking in on popping in and out. Okay. Keep working. Ignore the man behind the curtain.
Next lesson, you're first. I think you have some extra quotation marks in there.
Yeah, I just did that.
There you go.
I mean,
No, I think
In code and its output, what do the first 3 lines of the program do?
How are you guys doing?
Good.
We're doing well. We had a bit of trouble at the beginning sharing everything, but it ended up working out fine.
Okay, good. I'm
Yeah.
looking for your document that you shared it with me, right? I'm just looking.
Yeah.
Oh, here it is.
Yep.
I see it. Okay. Yep, I got 8 of them, so it's hard to see them all at the same time. I do have a big screen that I put them all up on. Okay. Well, let me know if you have any questions.
Thank you.
I think we're good for now. Thank you, though.
Okay, bye-bye.
Need 0.25 in QR for my requirement.
Okay.
Hey guys, how you doing?
good. We're just finishing up the forms at the end, but we finished the activity.
Okay, Oh, good. Okay. So, and it makes sense. You have any questions?
Yeah, no, it was pretty good.
Okay. Thanks. I will be back. I'll see you later.
All right.
And it'll just add like a space there, but you won't even be able to see it.
Okay.
How's it going, guys?
It's
Oh,
going-
hi. Yeah, we're chugging along.
Okay. Just checking in. All
Yeah.
right.
Thank you.
Probably just be a few more minutes. I'm going to pull everybody back. Okay.
Oh, how?
I'm sorry. I missed your question. I was already on my way out. Yeah. ask-
Oh, I was gonna ask how much longer we have.
like
Like
5 more minutes.
how many? Sorry.
Like 5. Will that is that enough or
I
too
think
much?
we can do it.
Yeah, I think 5 is an ample. amount of time.
Okay. See ya.
See ya.
Yeah, I actually pulled you guys back a little bit. Did you guys finish? Yeah. I actually pulled people back a little sooner than I meant to, but where everybody will be back here in a second. Okay. I apologize. I actually pulled people back a little bit longer, sooner than I meant. But if you're wrapping things up, you can go ahead and do it on your shared document. I don't really want to put everybody back in their rules. I hit the wrong button. Okay, so let's talk about it a little bit. All right. So looking through my groups here. Hang on while I get myself orientated. Well, I know some of you guys are finishing up too. Where is my Podial? Here it is. Okay, so Tori, I know you're spokesperson. Phineas, on 1, tell us what you found. What did you guys find of interest there on number 1?
Okay, so for the first one for A, because the text is within the quotation marks, it just prints hello, comma, my name is Pat. And then for B, because there are no quotation marks, we get a syntax error. And then for C, the backslash and N gave us hello, period, and then the next line, my name is Pat, which is a bit different from the other ones. So
Okay,
yeah, we
good.
just noticed that
sounds
without
good.
the quotation marks,
Right.
syntax
You
error.
gotta have, we learned we gotta have quotation marks, and that backslash N sent us to a new line. Isn't that interesting? Okay. So Ruby, what did you guys find out on number 4?
On number 4, so should I read out what all of the outputs were?
Well, no, you don't really have to do that. I can actually see what you guys did actually, because I got it right here. So I mean, what did you learn from this? I mean, what did you find out when you put quotes versus when you didn't, like on B and C there?
So quotes, when you put quotes around something, even if it's an operation that like the computer knows how to do, for example, 2 + 5, it comes out exactly as typed rather than processing the
Right.
operation.
Hence
Where
the quotes, right? It's
Yeah.
it literally quotes it, yes.
Yes.
Right, and then when you didn't have the quotes, it actually did the operation, didn't it?
Yes.
Now what about the comma? What did the comma seem to do?
The comma, I'm not exactly sure like exactly what it did.
Does any other spokesperson have a theory about what that comma does?
For our group, we found out that it created a space.
Mm-hmm. So basically, there's a space between age and 20, right? And so what you can actually do is you can put as many things as you want in the print, and you can put commas between them, and it puts them all out together with a space in between each one. Okay, good job. Now, hang on here. Achilles, who's a spokesperson of a group. Yes. Did I pronounce that right at all?
No, it's fine. I go by Aki.
Aki, that's right. Right. Okay.
Yeah.
So Aki, actually I have a really good friend named Aki. So I like that name. Actually, yeah, but basically we talked about 5. So what did the first 3 lines do in number 6?
Well, basically they were all comments, so they actually do nothing.
Right.
Function.
So why do you think you'd want to put comments into a program?
It might be useful for like other coders if they're reading what you wrote. You can leave like sentences explaining what you did. It can also give credit, like it does in this one.
Mm-hmm. So yeah, so it turns out comments are pretty important, just like you say, right? So, and in fact, they can actually even help you out, because when you go back to a program and you might say, what was I doing here, right? So we call this internal documentation. It's information we can put in a program to help us remember or to tell other people what's going on in the code. So we actually want to put comments in our code as a force of habit almost. Okay, so Tara, what did you do? Why don't you show us what you did for number 1? I'm going to let you share your screen and show us what you did for number 1 there, and talk to us about that.
Okay. Let's see. How do you share your screen again?
There should be a green button at the bottom of the Zoom screen. Yeah, you click that and then you pick the screen or window you want to show.
Okay. Oh, I don't have that updated to do that.
Let me see here. Huh. Maybe, oh, interesting. Okay, can somebody else want to try it? Somebody else have I mean, I can show mine, I guess, but mine doesn't fill in like yours. I mean, I guess, well, it's on a different computer. Let me see where Terry's at here. Is that in general, somebody else try sharing your screen. I just want to make sure that it's working. Nobody? Oh, here we go. Yeah, there we go. So here we go. So congratulations. So you did it in 1 line, so that's pretty nice, right? You said congratulations, new line you just created. New line, your first Python program. Yeah. There you go. Yeah, looks good. And good. Now, did somebody get number 2 done? And could they, if you want to stop sharing, if somebody could share their screen on number 2. Maybe Haley.
I will. Just let me give me a second.
Okay. And this is okay. It's okay that we're in this learning process here, so don't feel at all bad. you know, you guys are actually all doing really well.
There.
Okay. So very nice. So notice what she did and what that group did was they put in quotes the problem and then they did the computation after the comma. Very nice. You see how that worked? So, all right. Very good. Does anybody have any questions or any comments on this? Something that just still doesn't make sense and you want us to talk about some more? Now, by the way, hopefully everybody's been invited into the REPL class. If you haven't been, or if you're new, I want you to send me an email and then I will send you, you'll receive an email that will allow you to join the REPL class. I also want to encourage, you know, a couple new people have joined who haven't been here. And I would recommend you just come to my office hours because I don't want to spend more class time talking about things. But my office hours are on the webpage on cs.kenyon.edu. You go to the class, you look at my office hours, there's a Zoom link there. I'd encourage you to come to my office hours. And we can talk about other mechanics in the class that you may have missed. And so let me share my screen here. I think you guys are going to be looking at me running REPL now. So now you guys have all now gotten to experience REPL. Now, so basically, you can use REPL on your own account. And so when you go in, you can always hit plus, and then you can pick Python, and you can always get a new program. I'm not sure why it didn't come up. Let me try again. We hit Python, and we can always name our program whatever we want. So I can call this demo for day 2 or something, right? And I can create that REPL. And why they call it a REPL, I have no idea. But we see that we have this programming environment. Now we'll learn more about this later, but it turns out that this shows any files that we have. And this is a file with our program, right? And so this is the program, and we can write long programs here or short programs, and we can run them. Now, just to kind of give you an idea, like if I go out here to my REPLs, I can actually see a list of all the REPLs I've made. And for example, actually, I don't want to show that one because that's C++. That'll just confuse you. Let me find a Python. Let me find a REPL I can show you guys. You've all heard of the game Hangman. So here we go. Here's a game that plays Hangman. Notice we have a nice long program. We're going to learn how to write programs of this level of complexity, right? And here is a whole bunch of words to use in the Hangman game. And I can run the program, although not right now because it's going slow. Oh boy. So here's I wonder if it's, you know, this actually brings me to something I wanted to talk about, and that is if you want to get a better service in this program, you can temporarily pay $7 a month. You don't have to do this, but it's going to be more reliable than you do. And you would upgrade to do that. You have to have a credit card. Now, you might say, whoa, he's asking me to spend more money. just keep in mind that, you know, $7 a month for 4 months is what, $28, and you don't have to pay for a book, okay? You know, I wish that I could just give you hacker capability, but I'm recommending that you do that. You know, and you would just probably want to do it monthly unless you think you might want to use it a lot. So I wanted to mention that about REPL. So now the thing is when you join the invitation, you actually go into this class. And when you're in the class, you can solve problems. And so, and I want to show you a little bit about that, because that's one of the things that we're going to be learning how to do. Here is a program. Here's what a problem looks like. And the way a problem looks is it's got some starting code. And then if you click on the files, it's got this readme.me. And this gives you, no, that's weird. Okay. This gives you, actually, I guess we don't have to do that if we look at the markdown over here. This gives you the problem. And it says, write a program that takes 3 numbers and prints their sums. And then here's the sample input, here's the sample output. And so we're going to be doing lots of these. So here's a problem, here's some code. Now let's see what this code does. This code says A equals int input, B equals int input, and then print AB. When I run it, it's actually asking for a number. And so I type in, let's say 3. Let's type in 4 and 7, and it prints out their sum, 11. Now we don't know how to do that yet, but I'm just bringing this up because I'm wanting to show you that in this course, we have a ton, of these problems, and they're kind of fun. You go in there and you try to write the code to solve the problem. And then when you're done, you can click a button and it will test your solution and tell you whether you got it right or not. And then when you get it right, actually I'll solve one. I'm going to show you the solving problem. And then you'll have to do it in your own. But so clearly this asks for 2 numbers and prints the sum of 2 numbers. But if I look at the, if I click on the README, it says, boy, this thing is wonky. Sorry, they recently changed all of this and I can't keep up with it. Oh my goodness. Anyway, this is the problem, but it was supposed to show, apparently it's buggy, which is annoying. Okay, so anyway, here's the problem. It says write a program that we type in 3 numbers and then it types out their sum. Okay, so you don't know how to do this, but I'm going to tell you, all we really have to do is add a 3rd input here, and I'm going to make that C. And I'm going, I'm going to say A plus B plus C, and I'm going to run it. And sure enough, if I do 5, 8, and 2, I get 15. If I run it 6, 7, and 8, I get 21. If I do 1, 1, 1, I get 3. Seems to work. Then what I do is I click on the tests and it shows some tests, and I can actually run one of the tests, and this test has -5, 180, and 17, and the output should be 157. So I can actually look at the tests. If I run the tests, it sees where it passes them. Tests pass. Now, if I had a bug in it, so for example, if I accidentally did this and I run the tests, they fail. So you keep modifying your program until you can run the tests. Now you can actually, by the way, create your own tests. And then once you get your program working, we run it no, not run it. We run the tests, bam, 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 pass. Then you can hit submit. Now mine doesn't have a submit button because I'm the teacher, but you're gonna have a button that says submit, and that's like turning it in. And after you pass your tests, you turn it in, and then I can go in and see that you have done the problem. Okay, so that's REPL. Now, just in general with REPL, you can always create new ones. You can always, although, all right. And then you can start writing programs, and it will keep track of your REPLs. Which is what we kind of learned about today. So you're going to be using this environment a lot. All right. So now, maybe that's not what I wanted to do. What I want to do now is I want to go back to, how much time do I have? I just have 8 minutes. Okay. So I want to talk a little bit more about some of the stuff we've been learning. And let me get this off of here. So when we talk about programs, it turns out programs are made of objects, data objects. Data objects are how we represent things and where we store things. And it turns out that there's different types of objects. There's something called scalar objects, which are things like numbers or strings, the things that we see in quotes. But there's also non-scalar objects, things that can be more complicated, like a list, for example. And so we're going to be learning about all these sorts of things. So the scalar objects that we have in Python, the types of things that we can work with, are integers, floating point, bool, something called a none type, something that doesn't have a type, believe it or not. So for example, int represents integers. So anytime you have a number in a program that's just an integer, a number without a decimal point, we call that an int. If we have a number with a decimal point, we call that a float. If we have, it turns out we can have true or false, and this becomes pretty important. We call that a bool. How many of you guys have heard of the term Boolean before? Okay, turns out Boolean was the name of a mathematician, George Boolean, and he kind of came up with these notions of how to do things with true and falses. So we call the data type bool if we want to represent whether something's true or false. And we can literally do that in a program. We can literally say things are true or things are false. Now, it turns out that, let me get out of here for a second. When we're in REPL, we can actually find out the type of things by typing in type. If I say type 3, and I run that, well, actually, I'm going to have to say, put that in a print statement. And it says class int. If I say 4.332, it says class float. If I say Kenyan, it says string. If I say true, it still says string because I put it in quotes, and everything in a quote is a string. If I do just true, it says bool. Isn't that interesting? Now, another thing I want to point out is this is where we can write lots of lines and then we can run them. Like I can type in print, 4, and I can type in print 4 plus 67 plus 1.223, and I can now run that program. Now this is what we call the console, and it's where the output comes from when we run the program. But it also has an interpreter built in. For example, I could do print over here, and as soon as I hit return, it runs it. I could say print and it runs it. Not only that, I don't even have to put print. If I type in a 4, it says 4. If I type in 4 plus 5 plus 6, it prints out the sum. If I type in Kenyan, now I can't do that over here. If I were to put in 2, 3 plus 4 plus 5 and try to run it, it's going to say, it's not going to do anything because that's not a valid program. I have to put it in the print statement. But over here, I don't. Now, why is that good to know? Well, if you just want to test something out, you want to say, I wonder what happens if I do high plus 5. It says you can't do that, okay? Because we already talked about that. That's not a correct syntax. But if I do 6 plus 7, sure enough. In fact, I can do a whole string of these. Whoops. No, I accidentally put a parenthesis in there, so I had to put it in parentheses. But yes, it worked. Okay, so feel free to play around with this all you want. And after you leave, when you come back in, you can always go to My REPLs and you can see the work that you've been doing. Like here's demo, I can go back to there. Okay, so that's all for today. If you're new or you're struggling in any way, tomorrow is, what is today? Thursday. Tomorrow I have office hours from 8 to 10 in the morning, and then I'll have office hours again on Monday from 1 to 3. So what's due for next Tuesday is there's going to be a quiz 2. You're supposed to read these chapters in the book. Again, come to my office hours or even hang around after class if you're new to the class and need to talk for a second. And there's the 1930s essay is due on Tuesday. Okay, 200 to 300 word essay on something that went on in the 30s. And again, remember, you can start getting your information by going into the timeline for the Computer History Museum. Okay. It's 4 o'clock, so I'm going to let you guys go. I'll hang around for a few moments if anybody needs to talk to me for a second.
Thank you, Professor.
Thank
Thank
you.
Thank you.
Thanks for your attention and hard work.
Thank you.
Hi, Professor. I was actually going to stick around too.
Yeah, I saw it. Yeah, of course, we had the email interaction.
Yeah, we had been emailing. I'd be happy to stop in for office hours tomorrow. I'm free from 8 to 10 also. Okay. Can I just pop in anytime with that link?
Yeah. I'll be around. And then again, so you should go to the cs.kenya.edu and before you do that and kind of read through the syllabus, and then we can talk about things. Okay.
Good. Okay, that sounds good.
Did you get into REPL yet?
So I'm in and I have an account, but I'm not in your class.
Okay, so I'm going to send you an invite right now while we're talking. That makes sure I don't forget. Okay, manage team members. There you go. You're invited.
Terrific. Thanks so much. All right, so I'll go ahead and look over the syllabus and get ready for office hours tomorrow.
Sounds good. Glad to have you in the class.
Thank you, Professor. Yeah, you too. Take care.
Okay, bye-bye.
I just had one question. So we're supposed to fill out